Okay, think about angles for a second. They can go on forever, right? Positive, negative, spinning around and around to 720 degrees, 1080, and even way, way beyond. So how on earth do you manage an infinite list of angles in a way that actually makes sense? It sounds super complicated, but the answer is, well, it's surprisingly simple.
So that brings us to the big question for this explainer. How can just one simple concept wrangle any angle you can think of, no matter how huge or tiny it is? The answer is really elegant, and I promise it's going to make your life in trigonometry so much easier.
And the solution is the reference angle. The best way to think about it is that every single angle out there has a little acute cousin that lives back in quadrant 1. This cousin, we're going to call it alpha, is just the smallest, sharpest angle your angle's terminal side makes with the horizontal x-axis. That's it.
So what's the secret to finding this cousin? It all comes down to what we call the bow tie method. Seriously, no matter which quadrant your angle lands in, you always form a little right triangle by connecting back to the closest part of the x-axis. And when you picture doing that for all 4 quadrants, you get a shape that looks just like a bow tie. This one visual is the key to everything.
So, with that in mind, let's build our bow tie toolkit. These are the quick and dirty formulas that will let you find that reference angle, that alpha, no matter where you end up on the unit circle.
All right, let's start with the easy one, quadrant I. If your angle, theta, is already nice and cozy between 0 and 90 degrees, well, congratulations. It's its own reference angle. So the reference angle for, say, 20 degrees is just 20 degrees. Alpha equals theta. Couldn't be simpler.
Okay, now let's see how this works in quadrant 2. Here, your angle is between 90 and 180. The question we're always asking is, how do I get back to the horizontal x-axis? In this quadrant, the closest part of that axis is at 180 degrees. So our formula is just 180 minus our angle. For 150 degrees, that's 180 minus 150, which gives us a reference angle of 30 degrees. See?
In quadrant 3, we've swung past 180 degrees. But the logic is exactly the same. The formula just flips around. This time we ask, how far past 180 are we? So the formula becomes our angle minus 180. If we have an angle of 220 degrees, we just do 220 minus 180, and we find out its little cousin is 40 degrees.
And that brings us to the last piece of the toolkit, quadrant 4. We're getting really close to a full 360-degree rotation. To complete that bow tie and get back to the x-axis, we just need to know how far are we from finishing the circle. The formula is 360 minus our angle. So for 300 degrees, it's 360 minus 300, which gives us a 60-degree reference angle.
Okay, toolkit assembled. Now let's put it into action. A couple of quick examples will show you just how smooth this whole process really is. Let's find the reference angle for 200 degrees. Step 1. What quadrant are we in? Well, 200 is bigger than 180, but less than 270, so that's quadrant 3. Step 2. Grab the quadrant 3 formula, which is theta minus 180. Step 3. Plug it in. 200 minus 180 gives us 20 degrees. Boom, done. Now what about radians? They always seem a little trickier, right? Well, check out this quote. It points to an awesome shortcut. From most of the radian fractions you'll see, you can just look at the denominator to figure out the reference angle. Seriously, it works like 99% of the time.
Let's test it out on 4 pi over 3. Using the shortcut, we just look at the denominator. It's a 3, so our reference angle should be pi over 3. But let's check it the formal way, just to be sure. 4 pi over 3 is a little bigger than pi, which is 3 pi over 3, so that puts us in quadrant 3. The formula there is the angle minus pi. So 4 pi over 3 minus pi, yep, it gives us pi over 3. The shortcut worked like a charm.
So what happens when you get a giant angle, like 400 degrees? First of all, don't panic. The first step is always to find its coterminal angle. Just subtract full 360-degree rotations until you get a number between 0 and 360. So, 400 minus 360 leaves us with just 40 degrees. And since 40 degrees is in quadrant I, well, its reference angle is just 40 degrees.
Okay, we've seen how to get this right. But now we need to talk about the one critical piece of intel you absolutely need. The single biggest mistake that students make with reference angles.
So here it is, the golden rule. Always make your bow tie connect the horizontal x-axis. Your reference points are always 180 or 360. The mistake is trying to measure from the vertical y-axis, from 90 or 270. So for our 200-degree angle, you might be tempted to do 270 minus 200. Don't do it.
It's always back to the horizontal. Remember the bow tie. All right, so why did we just do all this? What's the big payoff? Well, this isn't just some random pre-calculus topic. This concept pops up in the real world, and it is absolutely crucial if you want to succeed in higher-level math.
For a real-world example, just look at solar energy. To get the most juice out of a solar panel, you need the sun's rays to hit it dead on at a 90-degree angle. As the sun moves across the sky, engineers use the angle of incidence, which is basically just a reference angle, to figure out exactly how to tilt the panels all day long to keep them at peak efficiency.
And looking ahead, this is a total must-know for calculus. When you start solving trig equations, your calculator is only going to give you one answer. It might tell you the answer is 30 degrees. But because you know about reference angles, you'll know there's another solution hiding at 150 degrees. This is how you find all the possible solutions, not just the easy one the calculator gives you.
So there you have it. You've officially mastered the idea of an angle's acute cousin. You've seen how one simple idea can tame a literally infinite number of possibilities. And that kind of leaves you with a final thought, doesn't it? What other elegant, powerful shortcuts are hiding in plain sight in math, just waiting to be discovered?